We will conclude acid-base chemistry by talking about titrations. So here is the experimental setup for a titration, where we have a flask that has an analyte, or basically a solution with a known volume but an unknown concentration. It could be an acid or a base. And then our titrant is usually placed in the burette, and we know both the volume and the concentration of the acid or base. So we use titration by titrating an acid or base with known concentration and volume into an analyte to determine the unknown concentration. And that point, the point at which we can determine this is when the moles of our titrant is equal to the moles of the analyte. So there are two types of titrations that we will talk about. One is a strong acid and strong base titration. So in this case, we are titrating against a strong acid. So this is what's called a titration curve for our strong acid, which is hydrochloric acid. Our titrant is sodium hydroxide. So we know the concentration, and we titrate in known volumes of our sodium hydroxide into a known volume of hydrochloric acid, but we don't know the concentration. So we can measure the pH with each volume increment of sodium hydroxide, and we get this titration curve. So notice that at the very beginning, right, where we only have acid, so we have a very, very low pH. And as we add strong base, our pH gradually increases. And then there's this point where we have this sharp increase, and midway through this point is our equivalence point. That is the point where the moles of hydrochloric acid is equal to that of sodium hydroxide. And then as we keep titrating, right, we end up with a really high pH where we mostly have base in our solution. So as I mentioned, right, at this equivalence point, the moles of our titrant and analyte are equal. And for a strong acid, strong base titration, we can simply just use M1V1 equals M2V2 to find the concentration of hydrochloric acid at this equivalence point. Now, it's slightly different, not slightly, it's very different when we are looking at a weak acid, strong base titration. So here we have a weak acid, acetic acid, being titrated against sodium hydroxide, strong base. So our pH is low, right, initially, but slightly higher than hydrochloric acid, which we would expect because acetic acid is weak. So we have this gradual increase, right? And our slope is different compared to our strong acid, strong base. But again, at some point, as we titrate in our strong base, we get this sharp jump. And the equivalence point is where the moles of our acetic acid is equal to that of sodium hydroxide. Now, so first I will say for a weak acid, strong base, the pH will always be greater than 7. Will always be greater than 7. And to determine the concentration of our weak acid, we actually look at the half equivalence point. So as you're doing this titration, right, you see where the equivalence point is. Half of the equivalence point, something interesting happens here, where the weak acid and its conjugate base are equal. They are equal. So we form a buffer region here. We form a buffer region here. And at this half equivalence point, the pH is equal to the pKa of our weak acid, right? And as I mentioned, the weak acid and its conjugate base concentrations are equal. Now, if we go to the left of the half equivalence point, right, where we have more acid than its conjugate base, our pH is less than the pKa. And if we go to the right of the half equivalence point, we end up with more conjugate base than its weak acid, and the pH is greater than the pKa. So we can use the Henderson-Hasselbalch equation to determine the concentration of our weak acid. Is there anything else I want to say? I think that's it. Okay, so let's talk about acid-base indicators. So when we're doing a titration, we add an indicator because the acid-base indicator is a weak acid, and it helps us actually visualize the equivalence point, right? So we have a theoretical equivalence point in the titration, but what we actually see in the experiment is the endpoint, and this is the pH at which the indicator changes color, right? So in our lab experiment, we'll work with phenolphthalein, so you will see this light pink color at the endpoint. So here's just a list of different indicators and the pH at which the pH range at which these indicators can change colors, because you need to choose the acid-base indicator that will cover the region of the pH at the equivalence point. So, rephrasing or saying that in a different way, you're choosing an indicator that has an endpoint that overlaps or coincides with the pH at the equivalence point. So here I'm showing a titration curve. The red curve is titration of the strong acid HCl, and then this purple curve is with the weak acid acetic acid, and both of them are titrated against with sodium hydroxide. For our strong acid, strong base, right, the equivalence point, any of these three acid-base indicators shown here will cover, right, we'd actually see a color change for our strong base, strong acid endpoint. But for the titration with a weak acid, right, which is here, phenolphthalein is the indicator, right, that where we will see a color change coinciding with the equivalence point. So this is why in our experiment we'll use phenolphthalein, right? Because we'll see it for strong acid, strong base, but that is the only one that we have access to, right? Where we'll see that change for a weak acid, strong base. So to conclude, the whole reason we do titrations is to determine an unknown concentration of some analyte, and we titrate against that analyte with a strong base, or it could be a strong acid. In this case, a strong base with known volume, known concentration. And we will pause there.